So now that we've seen some about how to color a knot, we're going to take a short digression to think back about rational tangles for a little bit, and what are the different schemes by which we could color a rational tangle. It turns out that coloring tangles is a lot simpler than coloring knots, and as a bonus, we also find out that how we color a rational tangle can actually give us a direct link into the one numerical complete invariant that we have for rational tangles, the tangle number. So we're going to try to do two things. First of all, inspired by the magic equation of the tricolorability condition that we know for knots, we're going to determine a scheme for coloring rational tangles that's an integer colorability scheme. So instead of having just a finite set in our crayon box to color with, we're going to have a whole infinite number of colors that we're going to work with. So we'll do that. And then we're also going to hope to connect the colorability of a rational tangle to its tangle number. This is the big surprise. And along the way, we're going to figure out how the colorability of rational tangles relates to the colorability properties of rational knots. So what might it mean to color a rational tangle? Well, we know what it looks like to tricolor a knot. That we have three colors to work with in our color box, and at every one of the crossings in our knot, if two of the colors at those crossings are X and Y, then we can determine the third color of the other strand that's incident at that crossing in some particular way, as long as it has the property that all three of these colors are either always the same, or they're always all three of them different. And they can vary from crossing to crossing in a knot, but every crossing has to have either all three of the same color or all three different colors. And over Z mod 3, we were able to construct an equation, x plus y plus z is congruent to 0 mod 3, which was the magic equation for tricolorability. Because this equation is met if and only if either all three of x, y, and z are the same, or all three of x, y, and z are different. And so that was the case when we were doing modular arithmetic over Z mod 3 to try and color a knot using just three colors, 0, 1, and 2. For rational tangles, what we want to do is to take that equation and remove the limitation of only having three colors to work with. So when we were doing this arithmetic mod 3, that meant that we only had three colors in our crayon box. And we could use this equation, given an x and a y, to determine the color z of the third strand that meets at a crossing. All we have to do, in principle, to move from three colors to infinitely many colors is to remove the limitation of doing arithmetic mod 3. In other words, use the same equation, just use it as an equation over integer arithmetic instead of Z mod 3 arithmetic. So that's a guess. That's what mathematicians call an ansatz. It's something that we're going to try and see if this gives us the properties that we're looking for. Because, after all, what this really means is that at each crossing, if I know the color of the overstrand, and I know the color of one of the understrands, so let's say my overstrand is 17, one of my understrands is 6, I can use this equation to determine the color of the other understrand. Just by multiplying the overstrand by 2 and subtracting the understrand, I can figure that out. The shorthand that I always use to remember this is that the overstrand is the average of the two understrands. And in that mindset, it's clear why if two of those are the same, the third one has got to be the same. And that if two of them are different, the third one has to be different still. It's not possible for three integers for the middle to be the average of the other two. The only possibilities for that are that all three of them are equal. Or if that's not true, then all three of them are going to be distinct, right? If the middle is the average of the other two. We should probably check to make sure that this is well defined, because any time that we're thinking about averaging, there's a possibility when we're dividing by 2 that we could get a non-integer result. But as long as we're always using the overstrand and one of the understrands to determine the other under, in other words, as long as we're using x and y to determine z, then we're never going to be dividing by 2, so we don't have to worry that one of these results is going to turn out to not be an integer. So this is always a nice, well-defined way of coloring. And we're always going to have that all same or all different property that we're looking for in a valid coloration. So let's see how it works for a rational tangle. So here's a rational tangle, just sketch it up. And if I want to use this scheme to color this tangle, I need to start somewhere. I need to choose a couple of colors to get my scheme started. And traditionally, I'm going to choose the colors to be up in the northwest corner of my rational tangle. So I'm going to choose them to be 0 and 1. Does this choice matter? It turns out that the answer is no, but we have to wait a little bit to see why. So for now, I'm just going to choose 0 and 1. And I'm actually going to choose 1 to be my overstrand here. The reason I want to do that, for no particular reason, but the reason I'm going to do it is to make sure that then my next strand ends up being a positive number. Right? The color of this strand is determined by twice the over minus the under. 2 times 1 minus 0. That's going to give me the color of this strand to be 2. And then I just keep going. I keep chasing through the rest of my tangle and figure out what the rest of the colors are. For instance, this strand right here is going to be twice the over minus the under, twice 2 minus 1. This strand is going to be 3. And so on, and so on, and so on. Until eventually I've run through all of these twists in the northwest corner of my rational tangle. Now I can go either here or here to try and determine more colors, but I have to go down here because this is the only crossing where I know 2 of the colors and I don't know the third. 5 is the over, 0 is the under, so twice the over minus the under is going to give me 2 times 5 minus 0. And so my next strand is a 10, the one after that is a 15, the one after that is a 20. And now I've looped around far enough to where I can find the color of this crossing, find the color of the strand on the other side of this crossing, as twice the over minus the under. The over is 6, the under is 20. Twice 6 minus 20 gives me negative 8. And then twice the over minus the under here gives me negative 22. And now I have colored each one of the arcs in my tangle diagram with a distinct integer. Notice I don't ever have 3 of the same integer meeting, although I could, but I have a valid coloration because at every crossing, all 3 of my integers are either all the same, which doesn't happen here, or it turns out that they're all different. The other thing I'm going to do with this picture is I'm going to very prominently label the colors of the strands that meet at the 4 vertices of my tangle. Right? The northwest vertex had 1, the northeast ended up negative 22, the southeast negative 8, and the southwest 15. Why we label those so prominently, we're going to come to appreciate over the course of the next few minutes together. So one of the interesting things about this process is that it turned out that I could go all the way from the northwest corner of my 0 and 1 that I chose at the very beginning. That was enough for me to be able to determine all the colors of everything else inside of this tangle. And the reason is that this particular tangle was presented in its canonical form, where I start with a bunch of horizontal twists, and then I attach some twists vertically, then I attach twists on the right, then I attach more twists on the bottom, then I attach more twists on the right, and so on and so on. So that rightward and downward only addition process, the canonical form of a rational tangle, makes it possible for us to do that. Otherwise, we may end up in a position where we don't have enough colors at a given crossing to determine what the next color should be. And then we might have to set up an elaborate system of equations to figure out, if we have a rational tangle that's not given to us in this nice canonical twist form, then probably we should try to put it in its twist form before we do this whole process. So far so good. We know that if we get a rational tangle in that form, we can determine how to color each one of its arcs with a different integer in a way that's going to make sure that we always have a valid coloration. What other information can we get out of this? Well, we define, or Kaufman and Lambrapalou in their paper, define what's called the color matrix for a rational tangle. And the color matrix is nothing more than the 4 colors that we find at the northwest, northeast, southeast, southwest positions, just packaged into a little 2x2 matrix. It turns out we're probably not going to do linear algebra with this matrix. We're just going to use it to be an array of numbers to keep track of those 4 colors. So let's pause here for a second and think not just about the tangle that we just colored, but let's think about the knot that would be associated with that rational tangle. The rational knot, which we would get by forming, say, the numerator closure of that tangle. What can we say about its colorability based on the colors that we just assigned to the arcs in this rational tangle? Well, there are 2 ways to turn a tangle into either a knot or a 2-component link. There's the numerator closure and there's the denominator closure. The numerator closure is the one that connects up the strands at the northeast with northwest and the southeast with southwest. So we add in these red connections here, and we now have what turns out in this case to be a knot. This is the numerator closure of the tangle G. Now, for this to be a valid coloration of that knot, we need to make sure that the strands which we previously colored 1 and negative 22 have the same color as one another, because now they are the same strand in this knot. Likewise with our 15 and our negative 8 down here at the bottom, those also have to have the same color as one another, because those are the same strand. And so we're going to get a valid coloration only if we color in an arithmetic system in which 1 and negative 22 are congruent, if they're the same, if we no longer see the difference between the number 1 and the number negative 22. and likewise 15 and negative 8. So in order for this to work, we need A and B to be congruent, mod some k, and C and D need to be congruent, modulo that same k. If we reduce all of the integers in my diagram with respect to that modulus, then we'll be in good shape. We'll have a valid coloration for this knot. One other thing that we notice, by the way, is that both of these differences, the negative 22 and the 1, and the negative 8 and the 15, the modulus that I could use to reduce the integers in this diagram in a way that no longer sees the distinction between 1 and negative 22 is the same as the modulus, which would no longer see the difference between 15 and negative 8. So that's interesting, that the difference between the northeast and northwest integers and the difference between the southeast and southwest integers is the same, 23, as one another. That's probably meaningful. So that's the story for the numerator closure. What about the denominator closure? The denominator closure is the one that I get by taking the tangle, and instead of closing up the tops and bottoms, I close up the left and the right. So I connect these arcs right here, and I connect those arcs right there, and I get the denominator closure of G. Now for this particular rational tangle, the denominator closure of G is no longer a knot. It turns out to be a two-component link. You should find out just by tracing this blue arc through and finding out that it comes back to itself over here in the southwest and northwest corners, and there's a separate component that links in over here on this side. So this ends up being a two-component link, but we can still ask the same colorability question. In order for us to have a valid coloration, what arithmetic system do we need for the denominator closure? Well, here we need the 1 and the 15 to have the same color, and we need the negative 22 and the negative 8 to have the same color. So whatever numbers that we use over there, they have to be the same. We have to choose a modulus that makes those indistinguishable. So 1 and 15 have to be the same, negative 22 and negative 8 have to be the same. And it turns out that just like in the numerator closure case, those vertical differences are also the same on the right side as they are on the left side. 15 minus 1, 14. Negative 8 minus negative 22, also 14, which also feels meaningful. Right? That somehow what we're noticing is that it doesn't matter if we look on the top or the bottom, if we're looking at the difference between these entries. The difference is the same across the top as it is across the bottom, and the difference is the same across the right as it is across the left. And each one of those is going to give me a modulus where if I reduce by that modulus, then I'm going to get a valid coloration of the associated knot or the associated link. Since 23 is a prime number, really my only option if I want to make negative 22 congruent to 1 and at the same time negative 8 congruent to 15, I should just reduce everything mod 23. And so that gives us a 23 coloration of the associated knot. Probably not super interesting, but at least it's something. Meanwhile, for my link on the right-hand side that I got from the denominator closure, I could reduce mod 14 to blur the distinction between 15 and 1 and negative 8 and negative 22. But 14 is composite. I could also get that same congruence by reducing by any factor of 14. I could reduce by 7. I could reduce by 2. And so that gives me a little bit more options for how to create a valid coloration of this two-component link on the right. Of course, we're going to have to throw out 2, because we know 2 colorations are not a thing. But the interesting thing is that at least this two-component link over here is going to have a 7 coloration, which we can figure out just by looking at the vertical differences, the right difference and the left difference, which are always apparently equal in this rational tangle. So far, we figured out that coloring a rational tangle using the integers can actually tell us something about the colorability of the knots and links that are associated with that rational tangle. But we've also noticed that there's some hidden structure here that we'd like to explore a little bit further. So what else can we learn about the process of integer coloration for rational tangles that can hopefully tell us something that we already know about how rational tangles work?